Hello everyone, welcome to my channel Chemistry is Fun. Today we will deal with a new topic, Dalton's law of partial pressures. Now see, we can have different gases and the compulsory condition is that the gases should not react chemically with each other, and if such gases are enclosed in the same container, they can intermix rapidly, and when they do so they will exert a definite pressure. But each of the gas in the mixture, they will exert their own individual pressure as if it is present on its own, means there is nothing else in the container. In that way only it will exert some pressure in the same container at the same temperature. So based on this, John Dalton gave a relationship between the pressure of the mixture of gases and the individual pressures of the gases which are present together in the container, and this relationship only is known as Dalton's law of partial pressure. So it's very important that this law is applicable to the different gases which do not react chemically and are enclosed in the same container. And this law states that at a given temperature, the total pressure exerted by two or more non-reacting gases, it's very important condition, they occupy a definite volume and is equal to the sum of the partial pressures of the component gases. That is, each component gas will have some partial pressure and the total pressure will be equal to the sum of these partial pressures. So based on this, we can have the derivation in the following way. If there are two non-reacting gases, N1 and N2 are the moles, means for one gas N1 number of moles of gas is present, for the second gas N2 number of moles is present. The pressure is P, volume is V and temperature is T. So we know that PV is equal to nRT. So here total number of moles will be equal to N1 plus N2. So PV is equal to N1 plus N2 into RT. This is the first equation. Now if we go for the partial pressures, then partial pressure for the gas A is equal to PA. So PA into V will be equal to N1 RT, because N1 is the number of moles of the first gas. So PAV is equal to N1 RT. Similarly, PBV will be equal to N2 RT. Now if we add these two, that is PAV is equal to N1 RT and PBV is equal to N2 RT. On adding, we get PA plus PB into V, that will be equal to N1 plus N2 into RT. This is equation number 4. From equation number 1 and 4, this is 1, this is 4. From these two, we get P is equal to PA plus PB. P is equal to PA plus PB because other things are constant. N1 plus N2 RT is on the right hand side. Here V is there. Only then P equal to PA plus PB. And if we divide equation 2 by 1, this is equation 2 by 1. We get PA by P, that is equal to N1 by N2, N1 by N1 plus N2. N1 by N2 is equal to total number of moles. So then it is the mole fraction. So N1 by N1 plus N2 is equal to XA, that is the mole fraction of A. So we can also say that PA by P is equal to XA. By cross multiplying, PA will be equal to XA into P, that is the partial pressure of A. PA will be equal to mole fraction of A into total pressure. Same thing we can get if we divide equation number 3 by equation number 1. We get PB equal to XB into P, that is partial pressure of B will be equal to the product of mole fraction of B into total pressure. So we can say that partial pressure of any component will be equal to mole fraction of that component into the total pressure multiplied by total pressure. In the same way, we can find out the relationship between total pressure and individual pressure. Now let's say there are two gases A and B. Okay, there are two gases A and B. At constant temperature, we take V1 volume of gas A. So for the gas A, volume is V1 and pressure is P1. For the gas B, volume is V2 and pressure is P2. So total volume V will be given as V1 plus V2. Total volume V1 plus V2. Total pressure is P. Total pressure is P. Partial pressure of A will be PA. Partial pressure of gas B will be PB. So we know that for the gas A, when they are mixed together, partial pressure of A into total volume will be equal to P1 V1. Similarly, for the gas B, partial pressure of B into total volume, that is V1 plus V2, will be equal to P2 V2. If we add these, we get PA plus PB. You add this. Actually, PA is equal to, we just shift this V1 plus V2 to the right hand side. So PA will be equal to P1 V1 by V1 plus V2. Similarly, PB will be equal to P2 V2 by V1 plus V2. So on adding PA plus PB, we get P1 V1 by V1 plus V2 plus P2 V2 by V1 plus V2. So we see V1 plus V2 is common. So on adding these two fractions, we get P1 V1 plus P2 V2 divided by V1 plus V2. And also PA plus PB is equal to P. So total P is equal to P1 V1 plus P2 V2 by V1 plus V2. So this is the case if there are two gases which are occupying individually V1 for one gas and V2 for the other gas. Then we can arrive at this equation finally. Now based on this we can see two numericals, then little bit clear concept you will get. First one is a mixture of hydrogen gas and oxygen gas exerts a total pressure of 1.5 atmosphere on the walls of the container. If the partial pressure of hydrogen is 1 atmosphere, find the mole fraction of oxygen in the mixture. Now see, so the partial pressure for hydrogen is, from the equation for hydrogen, partial pressure of hydrogen, that is given as 1 atmosphere. And P total is 1.5. So then for P oxygen will be how much? We have to subtract 1.5 minus 1. That is 0.5. Now mole fraction of oxygen. Will be equal to partial pressure of oxygen by total pressure, that is 0.5 by 1.5, that comes to 0.33. So this is the mole fraction of oxygen. Next, one more numerical we can have a look. A mixture of gases contains 4.76 moles of neon, 0.74 moles of argon, 2.5 moles of xenon. Now calculate the partial pressure of the gases if the total pressure is 2 atmospheres at a fixed temperature. Now partial pressure of neon will be equal to the product of mole fraction of neon into total pressure. So we have to find out first this mole fraction. That will be equal to the number of moles of neon divided by sum of number of moles of neon plus number of moles of argon plus number of moles of xenon, that is equal to 4.76 divided by 4.76 plus 0.74 plus 2.5. So the denominator adds up to 8 and numerator is 4.76. On solving we get 0.595 if we divide. So this is XNE, partial pressure of neon. Similarly, argon. Partial pressure of argon we will get by dividing the number of moles of argon by the total number of moles, that is 8. So for argon it is given 0.74 by 8, that comes to be 0.093. Next is partial pressure of xenon. That will be number of moles of xenon again by total number of moles, that is 8. Number of moles of xenon given is 2.5. So 2.5 by 8, that is 0.312. Now we got the mole fractions. So we can calculate the partial pressures by multiplying with the total pressure. So partial pressure of neon will be, we got it as 0.595, that is the mole fraction. That will be equal to mole fraction of neon into total pressure. That will be 0.595 into 2. That comes out to be 1.19 atmospheres. Similarly for argon, that will be mole fraction of argon into total pressure, that is 0.093 into 2, that is equal to 0.186. And partial pressure of xenon, that is mole fraction of xenon into total pressure, that is equal to 0.312 into 2, that is equal to 0.624. So in this way we can calculate the partial pressures of the component gases. I hope you all could understand the concept which I discussed today. Please subscribe to my channel. Thanks for watching my video. Please subscribe to my channel. Thank you all.